My name is Sein Jeung. You should have seen me throughout the workshop making jokes here and there. And yesterday in Town, yeah. I'm a PhD student working in the Berlin MoBI Brain Body Imaging Lab, and I'm also jointly supervised by Professor Christian Döller in Leipzig MPI and Kavli Institute in Norway, Trondheim. In this session, we're going to talk about importing, and it might come across as a little bit odd to dedicate a whole session about importing, because this is usually considered a super trivial part of data processing. But the reason we decided to include session was because this is where we can do a lot for open science and performing good data management. So we can do this by formatting your data in bits. This is short for brain imaging data structure. So I really appreciate that Klaus finds this important, and that everyone here is showing interest in this. Yeah. So with this, we move on to the overview of the sessions in day 2 and day 3. Laurens just showed you how to use lab streaming layer to record data. And right after having collected your data, you will have the data in .xdf format. And then before we can do all these super cool analysis on the EEG data and motion data and both things combined, we first have to import the data so that the format is recognized by EEG Lab and MoBI pipeline. And we do this in 2 steps. So first, we convert the source data to raw data in bits. And then from this bits data, we go to the set format. And it might look like a workaround, but we will talk about what advantages there are in doing this. So overview of the session. On the theoretical level, we're going to talk about what bits is. So many of you must be familiar with bits already, because there have been increasing interest in open science in general, and there are really, really cool talks given by really cool people. But I want to specifically discuss using bits in MoBI context. And for this, we zoom into 2 of the modalities, bits for EEG and bits for motion data. And it's true that we also record many other modalities along with EEG, not just motion. You can also use eye tracking or EMG, many other recordings, but because I am developing bits motion, so extension for motion data together with Julius Belzec, it's a great opportunity to stir up some discussion and get some feedback for this. And then its relevance for MoBI research, this might already be obvious at this point, because all the previous speakers were showing you all the fancy setups with many, many pieces of hardware and software. So data management is not a trivial matter for MoBI data. In the hands-on part, we're going to work on this small data set file, the VP24XDF. We're going to try converting this to bits and then importing this bits data back to EEG Lab. Lastly, there will be 1 slide about materials and guidelines to contributing to this, because many of the effort is community-driven and open source. So any kind of contribution is welcome. So it doesn't necessarily mean that you have to like create some materials and then contribute this, but just like even feedback or criticism would be really welcome. Yeah. So before we go into bits in neuroscience, we take a few seconds to bash astrophysicists. Something happened over 20 years ago. And as the title suggests, a super expensive $125 million Mars orbiter went out of the orbit. And it says it was a simple math error, but in my view, this is more like a metadata error. And what happened was that in a really big international projects like this, multiple teams worked together, and one team was assuming the metric system for the acceleration data that they were providing, and the other team just assumed that these numbers were in the English system of inches, feet, and pounds. And this small mistake was enough to blow up the whole project. And as it is quoted in the article, this is so dumb. But it can happen. Like if you think about all the complicated things that people deal with every day, it's really easy to not pay attention to these details. And if this slips out of our minds, it's quite scary because it can be really costly. And in neuroscience context, I'm pretty sure this happens too. If you're lucky, you will find it when you plot your data, or if you're a little unlucky, you go down the analysis pipeline and then notice this last minute. And if you're really, really unlucky, who knows how many mistakes remain in the publication. Yeah. So to resolve this issue within the neuroscience community, there was this article published in 2016 by Chris Gorgolewski and others. This is kind of suggesting a brain imaging data structure for fMRI data initially. So in this picture here, let me just configure my pointer. Yeah, like on this side, I have no expertise in fMRI, but this is the structure of data files right after data collection. So what I can tell from this is that I cannot tell much from it. So there isn't really a clear indication of which files they are and what they contain. And once you convert this kind of source data to bits, then it is more in a human readable structure. So it's already clear from the way the folders and files are structured what this means, what each respective file means. And by doing this, by imposing some restrictions on the way people name and structure their data, it supports the FAIR guiding principles for scientific data management. So findability refers to people being able to find data sets that use certain methods or have certain properties. And BITS supports this by providing rich metadata. Accessibility is slightly different. This is supported by data sharing platforms like what Joanna presented on day one. She was sharing her data on Open Europe. So these platforms support accessibility aspect. And interoperability means that when people work on the data that's being shared, it should be operatable without much human intervention. So it should be possible to use automatized pipeline on the data. And BITS does this by designating data formats for each modality. And reusability refers to the aspect that when data set is being shared, all the information that is needed to reuse the data has to be in place. So we zoom into now two different modalities. So BITS modalities, because this is a community-driven effort, you can find the specification here, bitsneuroimaging.io. And it's still being extended to many other modalities, not only brain imaging modalities, but also other physiological recordings and also animal studies. But for MoBI people, BITS for EEG and BITS for motion, these two are probably the most relevant. Yeah. And if you look at the BITS extension for EEG data, this came out in 2019. Maybe a few things that's worth noting here. The raw data format that's recognized by BITS is officially the brain vision data format and the European data format .edf. And what you see here and what's going to be used throughout today's session as an example is the brain vision data format. And this comes in 3 files. So .eeg is the data, and .vhdr is the header file, and .mrk is the marker file. And then for motion data, the raw data is coming in tab-separated values. So this is just a text file that's separating each column with tabs. And this contains continuous streams of position and orientation data. And some more in case you have say like magnetic field strength or joint angles, these are also falling under the category of motion data. And then some other interesting files, the metadata files, for instance, this channels.tsv file contains information about the channels. So it contains information such as units and sampling rates. And this can be stored easily as a tabular structure, as a table. And that's why it is coming in .tsv. And then non-tabular metadata comes in .json format. This is also just another kind of text file, JavaScript object notation files. Yeah. And then the extension for motion data is still work under progress. It is just one Google Doc where we put in ideas about how we should format metadata for motion data. And so as this is still in the making, there is still room for improvement. And if you don't like anything about this, then, or if you think something has to be added, then there is still time for you to comment on this document that I will share after the talk. Yeah. Okay, so with this, we now think about why we should do this for MoBI research. As I mentioned a little earlier, that the experimental setups are way more complex for MoBI research in comparison to other neuroimaging studies. Well, I mean, all studies are complex, but it's really easy for us to create a mess with all the, multiple pieces of hardware and software systems. So even within our group, we use different HMDs. So this one is Windows Mixed Reality headset. And this one's Oculus Rift. And for motion tracking, you can also use integrated things together with the VR system. So the controllers and the HMD, they are also tracked. Or something like leap motion or phase space that Klaus was showing earlier. And yeah, the EEG system is also a little special. So the move system transmitter and then the wireless Zotac backpack. These things can affect data quality or the way the data is stored. So it's important to document these and communicate this. And like in terms of motion capture, you can also combine marker-based and inertial measurement units in order to increase precision. So this is an example of two different motion capture systems being combined to collect data. And yeah, like anecdotally, you probably tried working on another person's data set. By another person's, I do not only mean that the data set was collected in some other lab, but even if it was collected by your colleague, it typically takes, I don't know, if you're lucky, one long meeting or multiple meetings sometimes, just to figure out what everything is and where to find certain type of data to navigate the structure of the data itself. So why this is typically the case is demonstrated in this example. So this is the water maze study that Klaus was also showing in the presentation yesterday. So I try to describe the setup in which I was collecting my data by saying something like this. So the participant walked 5 meters along the y-axis, and then they rotated the controller 30 degrees around z-axis. And then the final orientation of the HMD was 30 degrees around x and 90 degrees around y and 0 degrees around z-axis in Euler angles. Is this complete? Maybe not, because different researchers can have different imaginations about what this means, because people can picture, first of all, different configuration of spatial axis, and the rotation can be either clockwise or counterclockwise. And all these things, when you don't specify it, if you're lucky, you can guess it from the data. If you know something about the setup, you can guess it, but if not, then it becomes a problem. So the solution to this is to provide rich metadata. And this is what this can look like. So if you are describing an orientation of an object, you might say something like the following. So the object was rotated 90 degrees around X, 30 degrees around Y, 10 degrees around Z axis. So this is the Euler angle representation. In addition to this, you can specify the rotation rule, whether the rotation direction was following the left-hand or right-hand rule, and the order of the rotation, because this also matters. If you switch around the order of these rotations, then the object might end up facing somewhere else. And then the motion coordinate system, this field in the metadata refers to which axis was pointing which direction in the physical space. So RUF means that the x-axis positive direction was right, and the y-axis positive direction was up. And then the z-axis positive direction was forward. And it is analogous to the way we describe the coordinate system for electrode locations for EEG data. So like there we use more anatomical language like LAS for anterior, left, and superior, right? So it's kind of the same principle, but non-anatomical language. And then if you are using inertial measurement units, they also come with their own spatial axis, and it is quite tricky to communicate this in a simple way like this, because depending on what object is being tracked, it is not very clear what forward and backward means on objects. Like if you have a neuron, like which way is forward and which way is up, right? So for inertial measurement units, people typically provide images of how they were placed on participant's body. And we also plan to integrate a standardized way to list these image files and then indicate this in the table. So to integrate this process of having data in bits format, we use the following workflow. So from source data, before we go directly to set files, we convert this first to raw data in bits. And then the advantages of this, you can get your data out there, share this with others, and use data that's shared by others with more ease. And from tool developers' perspective, because you can expect how the data should look like, it becomes really easier to develop some analysis pipeline like this one. And if you have your data in bits, you can also use tools developed by others more easily, in assuming that the community is sticking to this norm. And yeah, and then we have a closer look at each of the steps, what the data looks like at each step. So say the source data, I think Benedict was asking a question in the previous session about having multiple streams together in XDF file and whether we can separate them. So this is done as you convert the source data to raw, and we have actually the function within the pipeline called bmobile_xdf to bits.m. And maybe here I should mention the definition of source and raw data. So people usually refer to raw data when they think about data that has been collected just now. But source data, in bits context, source data is the pure unprocessed data right after data collection. And raw data is minimally processed source data. And what this minimal processing means, I'm going to return to this in the session after this one. But to say briefly, it's source data that has been harmonized. So if you have different data formats and different modalities in one data set, they are not very uniform. So to give some coherence to your data, you need to kind of come up with a consistent vocabulary and consistent framework to encapsulate the data that you have collected. And reconstruction refers to complementing missing parts of the data. Like if you have occlusion artifacts in motion data, this has to be taken care of at this stage. And then conversion of the formats that is necessary to be conforming with it. And after you have done this, it's pretty straightforward to import the data to convert it to set file. There are many useful tools for doing this, and we're going to see how this is done. Yeah, just to reiterate again, data, when you have collected it, it is in this source data folder. You probably should have downloaded it already, ideally. So within the source data folder, there is an individual subject folder with some suffix and numerical ID. And then this is the data file, one single XDF file that's containing all of the data you recorded. And then after converting this to bits, you see that there are two folders for each subject now. So we separated the behavioral data and then EEG data. So behavioral data here contains the motion data. And then the EEG data has the actual EEG data plus relevant metadata. Yeah, let's move on to the hands-on part. And speaking of field trip, yeah, like I really like the scripts that's so that this function called data2bits.m. This one accepts multimodal data, and it's pretty well documented. So if you're interested, you can check out these documentations. And I also want to say that the example scripts that we show in the following slides, they're sort of the wrappers for the field trip function, but there are some special considerations for motion data at the time of import already. So standard XDF loader that's included in field trip, for instance, doesn't work very well with certain types of motion data. So we'll see why that is in the next slide. Yeah, so this is the function that I was talking about. It takes these things as inputs. And the first two things are required in MoBI configuration. There's just a struct that contains all the parameters that you want to use for importing or analysis. So if you just want to import data to bits, then you only specify the relevant fields that I'm going to show you. And the numerical IDs are literally the numerical IDs of the participants. And then there is a bunch of other metadata. If you really want to just import and not care about this, then you can also skip this. But even if you are not sharing your data, I find it nice to have it all documented while it's kind of still fresh in your memory. And this can also like make things easier if you want to publish your data later and then have it open source. So yeah, it's kind of like filling out a survey form. So it is just imagine this as somebody asking these questions about properties of your data set, like how it was required and all the meta things about the data, and then you are giving them the answer. So there might be many lines of codes that will be shown from now on, but just don't be annoyed by it. Relax and try to see it as filling out a form. Although I know that nobody likes bureaucracy, yeah, but it's gonna save you time, I think. So as I said, please open this script now. So in the folder that we shared, there is scripts folder, day 2, it's MoBI workshop, it's interactive.m. And once you have done this, then you configure the necessary tools by adding the path to your EEG lab. If you do this with your startup script, you don't have to. And then the data folder. I don't know where you save your data, but just add this path. And this data folder should contain the 0 source data folder, as I showed before. Yeah, so this is the exciting hands-on part. Yeah, I'll just, while you are doing this And then try starting the EEG lab so that it's initialized and adds all the plugins. I also want to say something about field trip. If this is included as EEG lab plugin, then you don't have to do anything. Initializing EEG lab, it will also add it to your path. But if not, then if you use this as standalone, then also add path to your field trip. And then these two lines here, they're just used for the workshop, so it's not part of the importing thing. I add the path to a specific function for loading the XDF data because although Lawrence already showed the data, we can now open the XDF file ourselves and then check it out. So there is another way to do this using XDF browser, I think. So I think XDF viewer and browser, they're different things. And the browser is nice, but I think it doesn't work for Linux OS. Yeah, so for Unix OS like Mac or Linux. So we're just doing this within MATLAB as much as possible. And I hope this was enough time to run all these lines here. And then you check whether everything is in place. You should be able to find the bmobile XDF 2 bits script if you added the bmobile pipeline in your folder in EEG Lab plugin. And it's probably, I don't know how many questions are in chat now, but with the number of attendees we have, it is probably difficult to address all the technical issues you are running into. So as we said before, talks, hands-on sessions, most of them are going to be recorded and be uploaded. So you can just follow this later and take more time if this doesn't work now. So no stress. And then you designate the number of index of the stream you want to look at, and then index of the EEG stream you want to look at. You cannot know this in advance, but I already know what was in. So this is just for visualization. So you execute these two lines as well. And then using the load XDF function, you try opening this file, the vp24 walk.xdf. Once streams is in your workspace, you should be able to execute these two lines to see what streams are in there. And they have really cryptic names: phase, space, underbar, rigid 1, 3, 8, 6, 9. You don't know which body parts there are, where the markers were on. And then there is the EEG stream, brain vision RDA, and the rest of the streams are all markers or events. And if you click, well, if you run this line here, you should also see the names of the channels within the second motion stream. That's in this format. So rigid body XYZ and ABCD and conf or confidence. What the XYZ ABCD channels mean, we're going to see this with some visualization. So the next lines are these here. If you execute this, you should be able to visualize the XYZ streams, the position streams. And how do we know these are position channels? We can't. You just have to know it. If you collected the data, you should have configured the LSL outlet, and this is the way you know it, or you document it as metadata. But once we visualize the streams, you can tell that the Z data is having the largest fluctuation, going from +6 to -6 and then back to +6. And from what we saw this morning and yesterday in the lab, you can tell that this is probably the axis that's going forward and backward because the participant was walking back and forth. And then the X position stream has, it's a really subtle thing, but to figure out how the axes were aligned with the space, you can also pay attention to the way it's changing as the participant changes their heading. So they go from +6 to -6, and then they change the heading, going back. And as they do this, they also switch the relation to the orange line. So the blue line is above the orange line, and then it's underneath. And this way we can kind of infer that this is the left-right axis. And then the Y channel that stays relatively consistent, this must be the up-down axis in the space. So that was a lot of guessing work. And then we try visualizing the orientation streams. These are saved in quaternions. So it is just a way to represent orientation. It has an advantage over the typical Euler angles, you know, around 3 spatial axes, 3 rotations, because it does not suffer from a problem with Euler angles called the gimbal lock. And in computer graphics or robotics, when the axes are locked using Euler angles, this leads to some problems. So quaternion streams are used very often for representing orientations. But this is not very human readable. So the current status of BITS motion is that we encourage people to convert quaternion data to Euler angles. And we're going to see how to do this in the next session. But first, let's leave it at this. Yeah, this is what the orientation stream looks like. Yeah.
Quick question, Sein. Do we need the BMobile XDF to bits at the moment?
Yes, so the plugin eMobile pipeline should be within the plugin folder of your EEG lab. So all the scripts that are on eMobile pipeline repository should be within the plugin folder of your EEG lab. Yeah.
And again, you find all the information, what to download and what to install, including all toolboxes and plugins.
Yeah, so this should be in the requirements. Yeah.
Okay. Thank you very much. Please go ahead.
And then you visualize the EEG streams. I plot the first 10 channels. And you can probably see when the participants turning their head, there is some kind of artifact. And the sampling rate was 1000, so it was roughly double the sampling rate of the motion data. So the basic configuration is like the following. So data folder, we already defined it. And then prefix for the participant folder and participant file name. So these are actually both the file name prefix. So in this case, it will be BP underbar. And then the folder that contains source data. And if you have multiple sessions, you can enter the names of your sessions, such as walking and standing or VR desktop. In this example, we just have walk session. So this is the thing that's coming after the numerical ID underbar and then the session name. And then you define the rigid body streams. So this is the way they are stored in the streams, the XDF streams. If you have freshly loaded it, they should match these names here. And finally, you assign some meaningful names to these streams. So the rigid 1 was actually the head, and then rigid 2 was actually the left thigh, and so on. So now you should be able to recognize the names. And then in case you have more detailed anatomical description of these body parts, I planned it to be like a hands-on activity, but we can skip this. If this is already enough for you, then you can just leave it empty or don't specify it. Then the resulting channels.tsv file. So in this behavioral data folder, you have channels.tsv. This is describing all the motion channels. And you will see these entries as columns name. So rigid body streams, these things are corresponding to entries in this column. And then rigid body names are the tracked points. And if you specify the anatomical terms, then this will correspond to this column here. And then some more configurations. So in certain setups, you only have parts of the streams in a session. So if you are comparing desktop versus VR session, the motion trackers might not be present in the desktop session. So this is just logicals that are indicating which rigid bodies are in which sessions, and you can just not have this field at all. Then by default, it assumes that every rigid body types are in every session. And then the units, in case you have different units depending on the session, you can also make like a cell array of units or orientation units in the corresponding order. And then the EEG keyword is used for identifying the EEG stream. And then bits task label corresponds to when your file name is in bits format, there is this entity key value pair that contains the name of the task. So if you do not specify this, then it also has the default value of default task. And this will only appear in the bits part. And if you convert it now to, or import it to set, then this will not be relevant. So execute the script up to this part. Yeah, so like I just wanted to show the units here, like radians and meters. And then comes the general metadata. So this is pretty straightforward. So the names of the fields are pretty intuitive. So it's just the description of the data set and which bits version you are using. It's an unofficial extension because motion is not officially the parts of bits. It's still being extended. And then other things, I omitted this because it's pretty obvious from the example what kind of things you have to enter there. So please simply execute this block of code until the line where it says general info task is bits config bits task label. Am I going too fast or too slow?
So I have no questions, no feedback
Okay.
regarding the pace in the chat. So this seems to be fine at the moment. If
Thank
not,
you.
please just mention that you need a bit more time.
Yeah, and then finally, there is some metadata about EEG, the frequency of power line and the reference electrode. Then comes the acquisition label. So this would be PH as short for phase space, and the manufacturer's model name Impulse X2. That's the system that we used. And then a little bit of a riddle to fill out the coordinate system where positive X indicates right and Y-axis is up and Z-axis is forward. In case you don't have the scripts open with you, then just think about this. And here's a little bit of a hint how to do this. So in case the positive X direction is right and positive Y is forward and Z is upward, then it's RFU. So just try to construct the string that would represent your spatial axis.
Sein, if I could interrupt, just some feedback. When you mention about lines, could you mention the line number in the code? Is that possible? If you
right
don't
now,
have it
it's
open,
not possible, but I could have done this. Yeah, I'm so sorry. Yeah.
Okay, no worries.
Please try to use find to identify the post. Yeah, but that's really great feedback. Thank you. Yeah. Next time I do this or do something like this, I will try to incorporate the line numbers. Yeah.
I can try and post line numbers in chat as we go because I have it open. So I'll do my best.
Oh, wow. That would be great. Thank you. Yeah. So up to this line. Yeah. So once you have done this comment in this line or commenting, commenting in, right? It's the opposite of commenting out. Then have it ready to be executed. Then once you run this script, you will see something like this in the JSON file. RUF, left-hand rule, and ZXY rotation. And then comes the participant data, which also includes a little bit of hands-on bit. So just don't look at this part and look at the final table. Here you enter the participant's numerical ID number and then age. sex and the group, whether they belong to the old and young group, and handedness, you can add custom columns. But if you do, then it is never clear what you mean by the column name, right? So the participants.tsv file contains this data you see here in the table. And then the JSON file explains all the columns. So if you have discrete entities like sex, then you describe it, and then there are levels M and levels F, and then the longer names of these things. And if you have non-discrete values, then you just specify the unit. So just try specifying an additional field for handedness. And suppose that we only included right-handed or left-handed participants, no ambidextrous people. So here will be additional 3 lines. So 1 line containing the description and levels. Yeah. Assuming that you did this, this will be the so to say the answer to the quiz. And you will see the outcome in the participants.json file like this. So handedness levels R and L. And finally, try adding a row for participant 24, age 30, female and right-handed. Like this. Or if you want to see the effect of what you are entering here, you can try entering weird things here, but I cannot guarantee if this is not going to throw any error. But you can enter something weird for age. So like as long as it's numerical, yeah. And just to see the effect of what you did. And then, yeah, so then you will see a participant TSV file that looks like this. And then finally, just run it for only participant 24. The rest, I don't think you downloaded all of the data, and it takes really long to import. So just run it for the participant 24. So this should have created the bits folder in where you contain all the directories. Yeah, so yeah, I hope this worked for everyone. So if you see another folder and click on this and see files that are in bits format, then you succeeded. And then the next step is to import data that is formatted in bits so that we can use them as set files. And you do something similar. So for this one, please open in the scripts folder, day2, 02 bits. Oh, sorry. Okay, I kind of merged them into like one script. So actually you should see this part at the bottom of your script as well. Yeah, it is the same M file, sorry. Because at the beginning, I intended to have separate M files for this part and the XDF to bits part. And I have to mention that here I will use bmobile bits to set. And this is sort of a wrapper for this EEG Lab plugin by Arnold Zulom for converting, importing and exporting bits data to EEG Lab. Yeah. So the configuration should be in place. Execute these lines and then just run it. That's it. So this, in my opinion, demonstrates how nice it is to have your data already in bits. So it is some work until you get there. So you need to like fill out some forms and do annoying things maybe, but in the long run, I think it's worth it. And I know that because essentially XDF is trying to deal with idiosyncrasies of your data set, it's difficult to automatize. So it's some manual work, but if you keep this in mind, that you probably want to specify metadata and convert it to bits later, then you can already think about this when you are designing new experiments and collecting data. Yeah. So that was the conclusion of the session. here are some resources for what I mentioned in the session. It's gonna be shared again as a PDF with all the links from other sessions. And yeah, thanks. All right, so the next session is motion prep. And this also includes a little bit of things that already happened while we were importing the data. So this might be going back a little bit in time. So when I was talking about the difference between source and raw data, there were some minimal processing performed on the data. And there are some special considerations for motion data. I don't come from biomechanics background. We just, so like the way I use it, I use motion data alongside EEG, and I primarily focus on the position and orientation streams. And this is not full-blown biomechanics oriented data. So from the limited knowledge that I have, I noticed some things, some subtle points that we have to consider when we do any kind of processing on motion data, especially maybe the orientation data. And here I would like to talk about these things. So going back to the overview. So yeah, in this session, we're going to talk about these two steps. So import and motion prep. Here we were looking at how we convert the source data to raw and then to Z files. And it is very difficult to not resample these data for time synchronization issues and also for harmonization between different streams. And then within the pipeline, you can also do some additional processing on the already imported data. And to summarize this, these are the things that are happening to your data when you are importing. So for position data, we remove occlusion artifacts. This depends on the motion capture system you're using, how the occlusions are represented and how severe it is. And then you resample the data. And for angular data, you convert them to from quaternions to Euler angles. And then because Euler angles have jumps between plus minus pi, you unwrap these angles before resampling. And then once you have imported the data, you filter and calculate time derivatives such as velocity, acceleration. This is the red part here. Yeah, so on the hands-on part, which is coming now, so we first do the hands-on thing and then move on to the theoretical discussions. So in the hands-on part, we're gonna try actually removing the occlusion artifacts and then resample the data. And then on the theoretical part, we're going to think about what happens to motion data when it's being imported and a little bit of conceptual question, what truly is raw motion data? And then some additional bit on the processing steps that is applied to motion data after being imported. So just to give you like a summary of what's happening to the data that we have plotted. So the source data, if you remember from the previous session, the position data looks like this and the orientation data looks like this. And once you convert the source data to raw data, this is the status of data that is being shared in bits. So you can notice that these lines, the vertical lines, they are there because occlusions, when the markers are not visible to the camera, these numbers are represented as zeros. And that's why there are these vertical lines. They are removed and the data is resampled. And resampling here is not upsampling or downsampling, but it is just that the data streams are resampled so that they can saved as a table. So if you have multiple streams from the same recording system, say the nominal sampling rate is 500 hertz, but some streams had, I don't know, 496 hertz and other streams had 504 hertz. In order to have these data in one table, you have to resample them. And this also takes care of the issue of irregular intervals between samples, which makes sampling rate not as informative for precise time synchronization. So that's why resampling happens already here. Just keep in mind that this is not downsampling or upsampling. It is just resampling to the, say, nominal sampling rate, or regularizing the sampling rates between the streams. So please, for this hands-on part, open this script. So in the scripts folder, there should be a folder called day 2, and then 3 motion prep, and this MoBI workshop motion interactive script. So once you have done this, you do something similar as what you did before. So replace these lines with your EEG lab and data path. And yeah, here we also use field trip, the load XDF function, just so that we can load the XDF data and compare source and raw data. So once you have ran these lines up to here, where you define the stream number, you can now load the XDF data by executing this line. And then the next line here, let me just also change the pointer. Okay, yeah, so this line here should display the names of the streams that are contained in the XDF file, just like we did. And then, oh, sorry, it's not gonna show the output, but it is defining the stream names. This is for plotting, actually. And then you load the .set data that you have already imported to bits. So if you were able to follow the previous session, you should already have the set files that are already in this 2_raw EEG lab interactive folder. And then now you have set motion data variable that you can plot and compare. And this is what it looks like. So in the source data, the streams look like this. So from here to here, it is just visualizing the streams from XDF and set files. And as I mentioned earlier, the occlusion artifacts are removed and it's resampled. And we're now going to try, so these 3 lines, you are now going to try applying these resampling and occlusion removal on the source data. So to see how we got to the second data that's now in set. So if you first, oh, sorry. So if you first define the position Y stream from the original data, you just do this. We are now going to focus only on the Y data that's coming up and down, which has the most prominent fluctuation. And then, I'm sorry, actually, this should be position Z, I think. Yeah, because this is the 3rd position stream. Yeah. Please just read this as position Z. Yeah, sorry about this confusion. See, like metadata is really confusing. So,
Sein, can I interrupt? Is
yes.
this something that people following along might need to change?
Sorry, no, don't change it. I just want to say that this is the Z stream that you saw before.
Okay.
Yeah.
Oh, I see. Okay.
Yeah, like I'm sorry about this. You don't have to change this now. Yeah. Yeah, so the times are the timestamps, the raw timestamps from the XDF file. And then the times rest, this is the newly constructed query points. So we're going to resample the stream to this new time points so that they have regular intervals. So first, we're going to try resampling using this interp1 function. So this is also the basis of filter resample function. So you're actually doing the same kind of resampling. And then once you do this, you can plot it you don't really notice the difference because it's just resampled from 480.5 to 480 or something like this. It's a not noticeable difference. But now what happens is that you try to remove occlusion artifacts first by detecting all the samples that are represented as zeros and then replace them with nuns. And then use this MATLAB function called field missing. And this returns the data that has been filled by means of linear interpolation. And if you plot this now, occlusion artifacts are not removed. It did something, but it's not nicely done. So we now go back to the position Y original data and then try doing the same operation with a reversed order. So you first find the occlusion artifact and then interpolate to fill. And then this is already clean. And from here, it's easy to resample and gain cleaner looking and resampled data. So to understand why this was happening, you can also run these two lines. You will see that the zero values contained in the original data and then resampled data, the number of zeros are different. And to have a more have a closer look into this, we can actually look at the occlusion artifact that is around 0 before all the operation. And once you resample, you can see that this is amplified, or like this introduced some kind of ringing artifact, especially if you used spline interpolation or piecewise cubic interpolation. There are some interpolation algorithms that can remove this problem, like nearest algorithm, which just takes the values of the nearest samples around these missing values. Then you're not going to run into this problem. But if you want to not be confined in your choice of resampling algorithm, it is better to first remove the occlusion artifact and then resample. So in the pipeline that I showed, this happens when we are converting the XDF data to bits. And in the configuration fields, there was this custom file that converts the motion data. So if you don't have anything to change, then you can just use this default function. And this is where all these detection of occlusion artifact and resampling happens. And if you open this default script that's included in the pipeline and modify this to your liking, and then configure this field, so which this will be just the name of the custom function, then you can kind of do whatever you want to with the motion data when it's being converted from XDF to bits. So yeah, this is the order in which it is done. Occlusion artifact is removed first, and then it's resampled to effective sampling rate. And then some more considerations for angular data. So I mentioned that the orientations channels are represented in quaternions. And when you convert them to Euler angles, this looks like this. So the vertical lines here are not necessarily occlusion artifacts. It is some more regular thing that's happening, that's coinciding with the way the participant is moving. And if you kind of put this next to the position data, you can kind of see what's going on. So when the participant is going from this to this direction, then the orientation, rotation around y-axis is near 0. And then when they change their heading and then go the other way, then the orientation changes. So these vertical lines are there due to the fact that when you represent angles plus pi and minus pi, so plus 180 degrees and minus 180 degrees, these are the same angles. So when there is a small jitter, it's kind of looks like it's jumping between this and this value, but they are actually the same value, jittering very, very slightly. So you can imagine that it will lead to similar problems as what we saw with occlusion artifacts. So what you can do is to unwrap the Euler angles, and unwrapping refers to removing these jumps by means of adding or subtracting 2 pi whenever there is a jump that is larger than a certain threshold. There is a MATLAB function that's used to do this called unwrap. And if you unwrap, then you can see nicely that the participant turned this way and then turned the other way and then kept turning in one direction. So like they were doing this turn over and over again. Like this, every time you see this vertical line here, they are changing their heading, and then the heading is maintained, and then they turn again and the heading is maintained. So for processing angular data, we first convert them to Euler angles, and then occlusion artifacts removed.
Sein, just a quick question. Yeah. These occlusion artifacts, are these specific to the hardware we're using, or is that just, I mean, occlusion can happen with any kind, but maybe you can elaborate a little bit on these.
Like, yeah, it is specific to hardware, and it can be more severe or less severe depending on how reliable your motion capture system is. And the way they represent the dropped values can also differ from software to software or from hardware to hardware. Yeah. So that's why we kind of give users the option to use custom files for this. So in the future, we might update these so that it is more modularized, and you can maybe like just pass some inputs pre-configured. But as it is now, you can just like look directly into these scripts and then configure this on your own to tailor it to the data that you have. Yeah, so like we convert from quaternion to Euler, and then occlusion artifact removed, and we unwrap them for jumps larger than pi. And then we resample to the sampling rate for having the data in tabular format. And then another, so this is the resampling that I just described. So resampling to effective sampling rate to match between streams within the same modality. So the EEG streams, they still keep the 1000 Hertz sampling rate, but all motion streams belonging to the same tracking system, they are all resampled to one of the sampling rates. So in the scripts, we use the stream with the highest sampling rate, and all the other streams are synced with the motion stream that has the highest one. And then we now resample for the purpose of saving disk space. So this now happens in the form of upsampling or downsampling. So we downsample to 250 Hertz when we are converting or importing data set in bits to set. And this you can configure this on your own. It's one of the configuration fields. And now, because this uses one single sampling rate for both EEG and motion streams, they should match. The samples have to match between EEG and position streams. So this is the question that I've been asking. What truly is raw motion data? It is by definition unprocessed or minimally processed due to file format conversion. So including harmonization, reconstruction, and conversion of the data. But it's very difficult to not process motion data before sharing. The operations like resampling or removing occlusion artifacts, or representation system conversion, removing clock jitter, this also is some kind of processing, and this even happens when you are using load XDF. And then in some systems which have markers assigned to multiple individuals, the identities of these people can be swapped if you're using some software to do this already at data collection. And if you have multiple markers present, the identities of these markers can also be swapped. And it's best when you deal with this before you share the data. But is this really raw data? And I think my personal opinion is that this should actually count as minimal processing, because I don't really see any like explicit downside to it. But I do think that there should be a systematic way to document how it was minimally pre-processed before being converted to raw data.